Hey everybody, this is Larry, this is me going with Q4 of the weekly contest 448, find sum of array product of magical sequences. Hit the like button and subscribe and join me in Discord, let me know what you think about this one. So this one I actually thought was, I wouldn't say easier, but more grindable for me. I think this problem is really hard to read, to be honest. If you watch the live portion, you'll see that I spent like 5 to 10 minutes just reading this problem correctly. But I think one thing that I would say is that there's a lot of properties that you need to know for this one for maths, so that's probably why it is a little bit tricky. Okay, so the first thing that there are a lot of things to dissect, right? But let's dissect this statement one by one as much as we can first, and then we'll dig into it a little bit, right? The first thing is that so you have this thing, right? The binary representation of this thing is k-bit. So what that means is that so we have this one was a tricky for me to understand, but basically it's saying that given m bits, this has k set bits in this sequence, right? And of course, if sequence of I is distinct, then well it will always have m bits, right? And the reason because if they're distinct, then you just have binary numbers, right? So if you kind of think about it as binary numbers, then now you have like 1 and then 2 and then 4 and then 8. And then if we take any one of these, then it adds 1 bit to the final answer, right? The reason why this k-bit thing is weird is because, for example, if you repeat, then now that's a little bit tricky, right? Let's say sequence of O is equal to 1 and sequence of 1 is also equal to 1. Then now the sum of this is going to be so 2 to the 1 plus 2 to the 1 is going to be equal to 2 to the 2, which has 1 set bit, right? So that means that k is equal to 1 in this case. Okay, so that means that if after finding and selecting m numbers with duplicates, we want k set bits at the end. Okay, not saying that we're not even getting to the point of how to solve for this yet. Just want you to figure out, just understand this part, right? If you don't understand what this means, what they're asking, then it's hard to solve, right? So so that means that in theory you can have repeats and stuff like that. And then the second part is this part, the product of things, which is fine, right? And then you have mod over all this stuff. For me, actually, honestly, I was a little bit rusty during this part. And if you watch the live portion, you'll see me work this out very deliberately and grindy. But basically the idea is there are two things, right? So a times b mod m is equal to a mod m times b mod m, right? Okay, I mean this one is obvious-ish, maybe not, but if you've done stuff it's obvious. But that means that now you could separate out the contribution to the things, right? And then the other of course is a plus b mod m is equal to a plus b mod m, right? And then there's another one which is also obvious, or just in general, even without the mod m, it's going to be a times b times c, say, and then if you want to add this plus a times b times d, then that's just equal to a times b times, well, c plus d, right? And this is the reason why this is important is because then now, if you see it this way, it allows you a way to do recursion, right? Because now, remember that we have only care about dirty things, but maybe that doesn't really matter. Is that now, you think about it in terms of recursion stack, we can rewrite this as like, okay, well, A, we get the answer B, and that we use 2, but then now we get the recursion of, okay, let's calculate C, where we skip C maybe, and then now, C plus, okay, we don't skip D, so then let's do D. And I mean, I'm kind of writing it and drawing it in an awkward way, but that's the way that I would think about it, right? And now I'm like, okay, from these here, I can do recursion in some way, because now we're able to figure out what the contribution of one of the numbers, right? And then the next thing I notice, you don't have to do it this way. This is the way that I did it. And I do actually urge you to watch what I did during the contest, because obviously I did not know this problem, but I think I moved in a very deliberate way. I mean, maybe certain parts I'm slow, so you can fast forward or skip 10 seconds at a time or whatever. But you can see that I said, all right, I want to solve this sub problem And then when I solve this, I'm able to get this, etc. And then I expand it a little bit more and a little bit more until I get the solution. And then the key thing to note is that, okay, well, I don't know how to solve it for any k yet, or I don't want to think about it yet. But what I notice is that for these inputs, m is equal to k. And what happens when m is equal to k? I ask myself is that if m is equal to k, can I if m is equal to k, can I figure out the solution for that, right? Knowing that if m is not equal to k, we're wrong. So basically, we want to solve a easier version of the problem that we're given, which is when m is equal to k. And when you watch the live portion, that is what I did. I go, okay, well, what does that mean when m is equal to k? So you have something like this, actually, right? So I abuse this by saying that, okay, if m is equal to k, that means that, well, each number can only be used once, right? Because if you don't, like if you do this, it requires 2 m's, but you used up only 1 k, right? And so that you'll never catch up. So for m to be exactly k, the only solution is every m is only used once. So I wrote some code, and I don't remember it because it was earlier. But here I just wrote, okay, index and m left, right? So the idea here with this memorization is that, maybe I'll write it outside so you get the syntax highlighting. Right? And if I write something like this, what would that look like? Well, if index is equal to n, then we're done. This is just going through the nums array, right? Otherwise, sorry. Oh, sorry, this is wrong. If n is equal to index is equal to n, we ran out of numbers. Then if m left is equal to 0, that means that we used all the m's that we care about. Then we return 1. Otherwise, we return 0 because there's no possibility, right? And keeping in mind that the reason why we return 1 is because we want to take advantage of something like this, where this is now 1. So that means that's going to be 1 times whatever's outside of it. So that's the identity, that's the base case, right? And 0 for the same reason, because then now it has no contribution to the answer, right? And then now it actually became a symbol take no take. You can watch the live portion. I probably do more deliberately. I might mess it up this time because this is actually not a reproduction, but it's just like a second try kind of thing, right? So take means that, okay, so we take this number. What does it mean to take this number? Well, index plus 1 is obvious, and then we used up an m, right? But what does that look like, right? So then now total is equal to num sub index times this thing, right? This being the rest of this. This num sub index you can think about as like this b, where all the parentheses is the recursion part, right? Of c and d and everything in between afterwards, right? So that's basically the idea. And of course you have the mod and etc. But I'm skipping the mod for now, right? So that's basically the idea. And of course you can only take if m left is greater than 0, or maybe, or m minus 1 is equal, something like that. Either way, right? And then no take is the same idea, right? We do, okay, then we just go index plus 1 and m left. And yeah, and we could just add this to that because, well, yeah, it's just basically you can think of it as 0, but then the current number has no contribution, but you want to add it to the rest of the contribution. And then that's it, return total, right? And now once you figure that out, so this would actually, I think anyway, maybe if I'm off by 1, I'm off by 1, but yeah. But this would give you the contribution of all these things where you have, well, a times b times ... times whatever, right? Times x, right? So this will give us all this contribution, right? Okay. But the problem with this one is that for this problem, we have to do, so this won't give you the right answer quite yet, not even for the 3 examples, right? The reason is because if you even look at this, you have to do the permutation, right? Because here we implement an ordering, we implement a structure going from left to right. So the ordering is going to be a question. But then now the thing about this is that, well, we start with index 0 and we start with m, but we just have to do it times factorial of m, right? Because M factorial gives you the number of permutations, and this will give you the answer for this will give you the answer for the examples. And actually, instead of me just saying it and hoping that it is right, let me let me run it for you so that I don't know, just in case I'm wrong too. Right. Again, for now we ignore mod, but I mean we'll put in the end just because then. I guess it's big M. Where's M? Oh. No, this is M, right? Oh, here. This is not real code. That's why. Okay. I don't know why it doesn't show the, oh no, that is the expected answer. Yeah, as you can see now it matches. And during the contest, when I saw this, I was like, okay, we're on the right track, clearly, right? But of course, then now you have to incorporate, well, what happens when you have, well, you have to incorporate K, right? And that took some time just because I was imprecise and stuff. But I hope that, you know, you at least get to this, or get your understanding to this point. This is an easy problem than what we had, and that's what I did during the contest. But that said, I just want to say, emphasize on the fact that it is, put emphasis on the fact that this is easier, but it's not easy. So if you struggle with understanding just this solution, definitely figure it out. You don't have to know this top part. It's not on the quiz. Just this part for now, right? Definitely make sure you understand how this became, right? It is take on the M and index, and I think the part, I mean, this part is DP and straightforward, hopefully by now. If you're attempting to solve Q4, this should be straightforward to you. Otherwise, you know, this part is a little bit trickier to understand, but you, as you say, you can think about this stuff as just putting these parentheses in this way. And if you kind of expand it out for a small number of things, you'll see why they kind of add up in that way, right? For example, let's say there's only 4 numbers. Let's just say, well, I'll do a small one just for you at home. But let's just say, okay, let's just say we have or we have 4 numbers, right? So let's just say 1, 10, 100, 1,000, right? Oh, but it doesn't even matter. Maybe we shouldn't do it. But we just have 4 A, B, C, D, right? So then it's gonna be A, times, kind of like if you think about the recursion, it'll be B times you know, like C. So yeah, this is so this is okay, let me rewrite this, right? So this is A going, okay, whether we should use B, so you have a B stack, plus where we don't use B, right? So that means that technically you still go on a stack, but then it will just be the next one, right? And then now the next thing is going to be C, right? And then now you go on stack, so it's going to be and technically I'm drawing this in a little bit awkward ways. Let's say that you have A, B, C, D, and you M is equal to 3, right? Then now it's going to be A times B times C in this thing, and then this C is actually technically there's a skip, right? And then now this will go to D, right? Something like that, if you want, and this is C times 1 times 1, and then now this is plus, right? This is skipping B, so it's going to be C times whether we do D or not, plus whether we do I guess we have to do C, because otherwise you run out of digits, or you need more digits, so something like that, right? And then now you can see that is A times B times C plus D, or I don't know if I'm visualizing this correctly, but you can see that when you kind of expand, if you add up all the things put back up, and I didn't do the skip A part, but you can see that you can it's equal to this plus A times B plus times D plus A times C times D, right? So that's just for this kind of like this. Yeah, right? And maybe you could even write this as like C plus 0, just to be more clear. So it's going to be C, which is C plus D, right? And then this is actually times like B, which is 0, plus C. Technically 0 times the recursion of it, but maybe we don't go recurse on it. No, this is the 0 version, so it'll be C. Yeah, this is the 0 version. I don't know. But you get the idea is that it all bubbles it back up, right? And this part is critical to visualize and understand, because the next part is going to get a bit trickier. Yeah. And then now we're trying to figure out, okay, the K part, right? So the idea behind the K is actually thinking about things like a binary number. It took me a while to kind of get to this precisely, to be honest, but it's just like, okay, now that we go one number at a time, what does that mean? Well, now we're just trying to add two binary numbers in a way, right? Because then now the state becomes, okay, so we have index, we have m left, but now we have to keep track of k left, because that's just things that we have to worry about, and then a carry bit, right? Because then now here what we're saying is that okay, index and m doesn't change. K left, I'm not going to explain too detailed. It's just how many k left you have, how many k's you have to implement, right? And then carry though is just, well, it depends on how we loop, right? And how we loop matters, because here, let's just say we'll skip the base case for now. But here we want to say, okay, well, we have m left. That means that we can use up to m left of the current number, right? So that means that num's index, we can use nums from 0 to m left times. And that's basically the idea. And then everything is from the implication of that, right? Because now, so carry means that, keeping in mind, so what does carry mean? So, okay, so this part I hope everybody understood. And this, of course, we just subtract from m left, right? So if you want to rewrite it, it's going to be index plus 1. That means that we're done with num sub index. We have m left minus whatever this I is, right? And then k left, we do some math on well, actually, we'll talk about this in a second, and carry bit. Okay, so k left, what is the impact on k left, right? Well, k left has an impact if the current bit is 1, right? We call it that we have this 2 to the, we call it that we have 2 to the, I don't know, 2 to the 0 plus 2 to the 1 plus 2 to the 2, dot, all the way, right? So we have a binary number that we, so then now we look at the binary number or the contribution of this formula one at a time, right? So we go, okay, what is the if num sub 0, how many times does it appear? If num sub 0 appears 0 times, then then that means that it just has no contribution. If it applies 1 time, that means that in this entire sum, it will have a 1 as a bit. If it appears twice as 2, which means that it has 1 carry but 0 bit, right? So that means it has 1 carry. And then now if it has 3, then it has 1 bit, which means that it affects k once and with 1 carry. And then if it's 4, then it doesn't affect k because now it's 0, but it has 2 carry and so forth, right? So that's basically the idea, is that k left, we subtract it if the current bit is 1, but of course carry placed in the data into a result, and that actually factors just like it would in a binary addition. And now we'll go over this, just go over the code real quickly, right? Or now anyway. Yeah, and we'll go over the base case in a second, but if k left is less than 0, we just I don't think this is possible, but given the way we wrote it, but we just return 0. Otherwise, we have a bit. So this is what is the current bit impact, right? And if that means that we have yeah, and you can kind of write this as equal to I mod 2 plus carry mod 2 mod 2, right? or maybe even just I plus carry mod 2, I suppose, right? And you could kind of see this, and the reason why this is the case is just that it is very much similar to like adding binary numbers, right? Hopefully this is still right. Okay, yeah, it's just adding binary numbers. So at the current index, we're having I version numbers of this, and then carry that. And carry, we'll talk about carry in a second, but that's just number of things that carry from the previous digits, right? And then now, if this is greater than equal to 0, meaning that we have a k bit to use, and we do have m bit to use because we only go up to m left, right? So this is good, and then we have to do carry sub I, carry plus I over 2, right? So this part is now the new carry, right? And this is, again, if you think about binary addition, this is what's left over for the bit, and this is the carry for the future, right? Because this is what's left over, and then we divide it by 2, which is a shift, so that we carry the new carry, right? So this is the new carry, and that's it for this part. And then the other part is, what's the contribution of num sub index, which is what we're modifying. Well, if there are I number of num sub index, that means that we multiply it I times, which means that we want the power of num sub index to I. And that's it. I mean, of course, we want the mod power so that the numbers don't get too big. So, but yeah. And then there's this inverse factorial. So I'm not going to go over this too deeply in terms of the math behind it. I'll go over the programming portion about it. But basically, for example, and this is something that you should look up. I'm a little bit tired, honestly, and this is very long, and there's a lot of things about it. But for example, if you want to count the we called that when we said, okay, how many permutations are there? Well, there's 5 factorial, right? Pretty straightforward. It goes 120 or whatever it is. But what if we have A, B, C, D, right? Well, this is going to be 4 factorial is it? No. Yeah, it's 5 factorial, right? But then within the 5 factorial, the 2 A's can permutate. We overcount because the 2 A's can permutate, right? So that's going to be 5 factorial over 2 factorial. And in general, and technically this is actually 1 factorial, 1 factorial, 1 factorial for B, C, and D, to be more specific, right? To be more general, maybe not more specific, but specific to this case. So then you have like A, B, B, D. It's going to be equal to 5 factorial over 2 factorial, 2 factorial, 1 factorial, right? And that's basically the core part about this one for I factorial, right? And okay, so we have to try to get this. And this part, I'm not going to go over this part just because it is, but do look up modular inverse, right? It means that because under mod, because we are doing things under the mod, you cannot divide things under mod, right? For example, if you have 200, this is a very basic example, but yeah, okay, maybe 13 over 13, mod 13, right? Maybe this is not a good example, actually. I forget how to do it. But in any case, my point is that modular, you cannot divide. You cannot divide, right? Because you have like 13. So for example, 13 over 11, let's just say mod 2, right? You cannot, I don't know, you can, 13 over 11 doesn't even mod 2 in general. But yeah, the idea behind a modular inverse is so that when you multiply by that modular inverse, you get the original number. So it's not that you want to divide 13 divided by 11, but it is that you want an f such that f times 13 will give you 11 mod 2, right? Something like that. But yeah, and I'm not going to go over modular inverse, but the idea here is that now instead of dividing by 2 factorial, 2 factorial, 1 factorial, you could convert this to just 5 factorial times the inverse of 2 factorial under the modular, right? And this one, I know that I'm going really fast because this is a lot of math to explain, and I don't want to make this like a 2-hour video going out every bit. You should look at modular inverse. It will give you some idea about what we're doing here. But this is the idea, is that, okay, now that you have this number, it will give you the solution, right? And of course, the reason why you can now put it in here instead of needing it to be out here and multiply is the same reason that we had here, right? Which is that I erased it, but the same thing of like, okay, now you can think of this as like just the same thing as we did before, even though it's with modular inverses. You think of that, okay, well, now A times B times C. You know, you want to add this with like, so let's say you have this as a modular inverse times another modular inverse that's like, you know, this. Maybe this is a 3, right? And then the way that you can rewrite this is that now you can group them to something like this, and then maybe even you know, times you put parens, right? 2 factorial times, and then now parens, right? And then so forth, right? So dot. I know I'm hand wavy a lot, but that's basically the idea, and you really have to be familiar with this. I a little bit YOLO'd. I was a little bit familiar with this, but that's how I kind of get off with this I factorial. And this I factorial is just factorial inverse, right? I wrote I for inverse. That's basically the idea. But here's the thing. And this is not really clean, by the way. You definitely should be doing better than this, because this will get you in trouble at some point. But the reason why it doesn't is because I is 50, and 50 factorial is not too big. And you only do it once because I only pre-process everything. And, you know, and this was not during the contest, so I didn't really care if I got a wrong answer, right? Like, it was during a virtual contest, but even that was done. So yeah, this was after the contest. But yeah, so carry bits. So yeah, I really like this problem. It uses a lot of things that you care about. And then the base case is just that if you have carry bits, well, they just, because now you could treat that, as we said, you could treat it as binary addition, and the rest of the numbers are 0 because you can't add more to it. So then now the number bit count, you just subtract it from k left, and if they're both zeros, then you're good. Otherwise, it's a 0, and that's it, right? What's the complexity here? Let's go over it. Index is 0 to 50. I want to say, I forget what it is. Yeah, 50. M left is also 50, I think. Oh no, 30. Okay, sorry. K left is up to 30. Carry can be tricky, but keeping in mind that M left can only be up to 30, right? That means that even if we choose 30 in one of the things, carry will be, in that case, carry will be 15, but it also gets divided by 2 every time, but let's just say 15, right? And then, yeah. And here there is so what is the time complexity, right? Time complexity is equal to number of inputs times time per input. Number of inputs is equal to n times m times k times say carry, whatever, right? And then each input takes O of m time. So this is going to be O of n times m squared times k times c, which is roughly, I mean, you do the math, but I'll do the math on my calculator as soon as it comes up. 50 times 30 times 30 times 30 times 15, it is going to be 20 million. So maybe it is actually a little bit smaller. Well, k has to be smaller than m, so there's some constraint here. And c, like I said, is not a full thing, but that's basically the idea behind this problem, and that is the complexity. And that's all I have. Yeah, let me know what you think. Thanks for watching. Difficult problem. And yeah, you could watch me solve it live during the contest now. Okay. Wow, I can't believe I solved it, honestly. But especially after all that, I was like, I didn't, maybe I have to not include the 1. Okay. I mean, clearly we're not going to solve Q4 in time. We have 7 minutes, but we'll do our best. We'll see. Okay, let's go. I mean, we'll solve it until after the contest or whatever. All right, mod. I should have gone that one earlier though, but I think I just kind of got confused about the offsets and stuff. Yeah, okay. Anyway, all right, let's go. It's magical if it has a length of m. Sequence of I is okay. That's a little bit weird, but it just means that it's binary representation has k-set bits. Still don't understand what this is going. Okay, fine. It's just hard to even read in general. Okay, the way product of this is you go to product. Okay, I have no idea what this problem is even asking. It's just so hard to read. But it is what it is. Maybe I'm glad I got the other one because I don't even know how to read this one. Okay, return the sum of array products for random. Okay, what's a magical sequence again? Magical sequence has length m, which we're given. The sequence of I is the binary representation of 2 to the 0 plus 2 to the 1 plus 2 to the 2. That's k-set bits. Okay. So plus. What does that mean? And you're given this random array nums. Okay, fine. Takes me. It's gonna take me until the end of the contest to even just read this problem correctly. But okay, so these are the number. Okay, I see. So this is the number of bits. So if that means that k of these. It's a little bit awkward. I mean here. Okay, so sequence. Okay, let me think. So with length n, so sequence has from 0 to n. Oh, so 0 to. What is nums? Oh, okay. So it has to be 0 to 4. Okay, so these map to the indexes. Okay. And then the representation of these. So that means that. What does that mean? That means that we pick k of these. Why don't you just say it that way? We pick k of these numbers. Wow. This is a very annoying to read problem. Okay, fine. The way product of this is product of sequel is equal to nums sub sequence of 0. So we pick what? What's m again? So we have m. So why doesn't this always have m bits? Or am I misconfusing this? Because I guess you can choose duplicates. Is that it? Okay, so maybe we can choose the same number multiple times, but it doesn't show up in here or here. Okay, 30 is interesting, but okay, right? Otherwise, okay, I guess so, because otherwise this has exactly m bits, right? If they're unique. Okay, anyway. Maybe we'll ignore that for now. And then the way product of this sequence is defined as this thing. So the number that is in, so you have some sequence in some order, and then you just product it, and then you just multiply the product of these things, and then you sum it, right? Okay. I hate that they don't give you an example about this, to be frank. Like, why would you? I mean, I get it, I guess. So, M, okay, so we have sequence of size M, N is 50. Nums is some big number, but I don't think that matters. It's just a. Alright, we have 2 minutes, so we're definitely not finished things on contest time, but that's okay, right? I mean, I didn't think I had a chance anyway, but especially after spending so much time on the other one. I still don't understand what I'm trying to do here, so. I mean, the only thing that this makes sense is if you can use the same number multiple times. And the idea behind that is that it's a little bit awkward. M is 30, what does that mean? M is equal to 30 reminds me of like meet in the middle type things, but I don't know. The k-bits thing is just awkward. I think the other stuff I could probably reason out, but I'm still trying to figure out how to handle the k-bit thing in a good way. This thing is just awkward too, but and it's go to 50, so it's like 50 choose 30 sounds a little bit awkward. I mean, the idea is still going to be like try to figure out the contribution, but it's just like a product, so I don't even know. I'm going to give it an honest attempt, but I don't know that I have any idea. How many people solved this? Oh, 168. Oh, now my thing is off the leaderboard. I hate that they do that. I don't know why they time it out. I think I had a screenshot, but yeah. So here, okay. I mean, that's why they chose M and K is the same thing as the example, but I'm trying to think whether why how to kind of okay, fine. What is M again? M is M the number of array element? M is the number of things in SQL. N is the number of bits, and there's another N that is the length of nums. Okay, so the MKN. Huh. I'm glad I got Q3 though, even if it took forever. I don't even know how to do contribution on this one, huh? Okay, so let's say even if we get this M, I don't know how to solve it. Alright, actually, maybe try to do that. Let's just say we have M and K is always equal to M. What is the solution? The solution is then just that we have N choose M things, right? In this case, this is 5 choose 2. That's why when this kind of shows up. Actually, it's not even 5 choose 2. Because the order matters. but okay, so let's say we have a bit mask. Okay, let's say there's DP and we have a bit mask. How would that look like? I guess the key observation is that when you add a new number to the bit mask, when you add a new number to the bit mask, it always either does not change the number of bits, or it adds the number of bits by 1, right? So then, so then maybe we have bit mask, we have count, number of count and bits mask for using for k, and then that's it, right? Maybe, but the bit mask can be big though, right? So that's the thing. I don't have any proof on this one, honestly, but and also we need m anyway. So we have m, we have count, okay, right? So yeah, okay, fine, like m left or something, right? So if m left is equal to 0, if count is equal to 0, then we return can I do that? I don't even know how to return in this case if it was DP. What is that? What does that even look like? Maybe 1? I don't know, but otherwise we return 0, right? Maybe? And I want to write something like this, but I don't know that that's correct. So then now if mask and if this is equal to 0, that means that there's no bit. No, I don't even know how that would work, because it can cascade. So I'm actually wrong on what I said about the observation, because you can have a thing where you add one number and then it just because you can go from, I was wrong, because you can go from like this, you add 1 to say here, and then now you go to here, right? So then that means that you, and that would use a lot of numbers. So then now the number of bit mask thing on that is not right. So okay, so I don't know that I can do it quite that way. Let's say we're trying to do index on the n, right? I'm left. This is a wild one. I don't even know how to think about this one, honestly. Yeah, honestly, I don't have any idea how to solve this one or even attack this one further. Like, how do you separate out the... And here I'm assuming m is equal to k. Am I? No, maybe not. I don't know. Alright, let's just assume m is equal to k. In that case, we have to choose m unique ones. Right? So then it's just take no tick. Okay. Yeah, and then just take no tick. So it looks like this. What would the take no tick look like? So you yeah, so then you tick. I think I have an idea with this take no tick. But I still don't know how to get the sum though. I think that's the other part. Okay. Well, okay, let's say we have tick no tick, right? Then now it's just you tick no tick, right? But then now how do you calculate the total from here? You have num sub index, that's a contributor. Is it, do you get the count? But it doesn't, it's the sum of the counts. I mean, the counts don't matter. Is that true? Like, what do we do with the take no tick? So we have a count. Let's just say we have a count of the number of subsequences that uses this. But you just multiply them, right? So it's almost like a shift based on the other thing. Okay, I mean, we have to, okay, first principles, right? So let's say we have a times a mod m times b mod m is equal, or the other way around really is what we care for, but right. And then now count is, well, this is obvious as well, so okay, right? No, I have an extra space. So how do we use this to okay, so let's say we have a count. Okay, so what does the sum look like? The sum, we have something like this. So we have like, okay, just some random things times c. Or okay, so let's say they're unique, then okay, fine, right? But the ordering, ordering matters, but then I could say we could do a combinatorial math on the ordering, but that gets trickier once we not allow m is equal to k, or k is equal to m, right? Yeah, because then otherwise you could just multiply that by n factorial or something, so that we have sum of this. I see. So then it's the total of, because here, okay, let's say we have two paths. We have like a times b times c times d, and then a times b times c times e. to merge them, we would have something like A times B times C times D plus E, right? Or to add them, you would get this. So I think that's fine. So then now, as a result, we just want maybe something like total is equal to do total right, and then return total. I think I'm going to solve this just for m equal to k because that's the examples anyway. So we could just to see if that's right. Of course, we can whatever for in a mod for good measure. If index is equal to n, or maybe even just like if whatever. If m left is equal to 0, then we return 1. Otherwise, we return 0. The one thing is a little bit awkward, but I think that's fine, maybe. Right, so then now we add that, and then this is this times num sub index, maybe? No. Okay, so this should be the tick no tick part, right? So tick, yep. So this is num sub index times this, and then we add it to the parts that don't. Then we sum it up. Okay, maybe that should be good. Let's see. Go 0 m, right? Okay, we have to close out parens apparently. Apparently a big thing in programming. Is that right? No, so it's not even right for this. Or even here, 28. So why is that not right though? So index, why is this not right? So 28. This plus thing is a little bit awkward, I think. Is it just 28? What's 28 times 28? Is that where I made the mistake by accident? Maybe that is 28 squared. So maybe I just made some mistake here. Oh yeah, because I have both of these whips. Okay, so maybe that's actually not bad. Let's see. So 28, 85 seems a little bit wrong. This is a little bit wrong. 85 is. I don't know if I just have to times it by n though. Or n factorial or something. Oh yeah, that actually I didn't use that. So here maybe factorial of m, because because we actually talked about that, but then okay, so is this right? So this is right. So I think my formula is mostly right? So yeah, so we can maybe work out something like that, and then now. Okay, now we have to do the K part. Actually, this is surprisingly not bad for, good job, Larry, right? But now we have to do the K part, right? Okay, so how do we do the K part? The K part is not that bad. It's just that we treat... okay, right? Basically you have carry bits, right? I think that's how I want to think about it. How do I want to think about it? I mean, that's basically the idea, the carry bits. Oh, but then you have to do the math on inverse factorial and stuff. Oh man, it is so annoying. Okay, fine. I mean, remember 0 to k we're done, which is actually pretty cool. But okay, so then now we have to figure out the k bit. I mean, carry is probably the way to go, right? K left, carry, maybe something like this. Where is that? That's 30, 30. I'm trying to think whether I can do another 50 loop on here. Alright, so 50 times 30 times 30 times carry. Carry should be at most 50, right? Maybe. Okay. Okay, so tick. So this is a little bit different now. So tick, no tick. Yeah, okay. Maybe I could do them in pairs, right? So tick 1. So then, okay, we tick 1, then it's just K left minus 1, because now we know that there's a 1 in this bit. If K left is equal to 0. And then there's no carry, right? And we can definitely take more than 2, just to be clear. But so no tick should be the same. I mean, we have to get carry into the current thing. So this isn't quite right because we're not factoring carrying in. We're just focusing on carry out. But maybe that's fine. Well, that's fine. It just okay, yeah, it just factors into K left, I think. Yeah, okay, fine. Right. Okay, take 2 and repeat, possibly. So that here, if K, this is also if M left. Oh, I guess I didn't do this one. I think I should have, but yeah. Okay. So if M left if we still have them, then we can do okay. K left does not change, but carry. We have 1 extra carry, right? So we take 1. Okay, so then now how do we deal with carry? So that means that we carry over things, right? So then carry we want to divide by 2, because now, oh no, well, we do eventually, but okay, what does carry mean to the left? K left, that's all it does, right? So that means that, okay, carry divided by 2, and then basically if carry mod 2 is equal to 1, then K left we decrement by 1. Well, depending on what we do, right? Okay, so then that means that parity is equal to 1, say, right? And then now here, yeah, we take 2. Wait, is this right? The thing is that we want carried forward, but this is actually messing this up because of the repeat part. Okay, it's either that or we do the max carry for like 5 things forward or something, but that's just awkward, right? Is it? No, maybe that's fine. Actually, I guess that's what this already does. But how do we do the repeat thing of the carry on the next carry while also calculating this into the parity? I guess we just have to factor this into the carry, right? So, okay. So, okay, so no tick carry. Carry just divided by 2. So that carry is updated. K left is plus carry mod 2. Okay, maybe that's how. So no tick. No, well, it's not plus. So okay, so right. So minus. Okay, fine. And maybe we have too many crazy things. So if K left is less than 0, we just return 0. Yeah. Okay, so take 1. Then you have this. Minus is minus this minus carry mod 2, I think. Right? And this again is carry 2 because we're done. Right? And then now this is fine. Kind of no, because then now when you keep on taking 2, you want next carry to be this, and then but when it ends, when you do it, then it carries back. I think the idea is right, or the approach is right. But we're definitely not doing it that way. Yeah, maybe this thing is too silly. Okay, let's not prematurely optimize this part. Let's just say we have, for I in range of m left plus 1, say. Then we just have I want to keep this because I'm gonna forget. But okay, for I in range of m left plus 1, we have say power of num sub index to the I power, keep it in mod power, times go index plus 1, m left minus I, k left, we have I mod 2 is the number of k left we have, minus carry maybe, minus carry mod 2, right? Okay, so k left minus I mod 2 minus carry mod 2, something like this. Carry plus, well, carry now we divided by 2 plus something like this, right? So if these are the same, I'm just trying to think actually. I think this is this. I messed up. Okay, so this bit. Okay, so bit is going to be 0. If I mod 2 is equal to 1, then the bit is going to be, well, we flip it. And then if carry mod 2 is equal to 1, then we also flip it again. So then, and then now we just, whether there's a bit on this bit, and then now carry is going to be half of that plus I divided by 2, right? Okay. I think this is right without the factorial bit. Maybe? I don't know. Let's run it real quick. Go. I just say k and 0. In theory, this should give us the same. Oh, I guess my timer is out. That's why it gives me the expected answer. But yeah, should. I mean, the factorial part. Actually, let's remove the factorial part just to kind of see. I mean, we should be able to get. I mean, this is just wrong. But we should be able to get the right answer. But well, like this should give us the right answer if, yeah. But this is where's m left is 0 0. Okay, n carry is equal to 0. Well, n k left is equal to 0. Oh, that is okay. So I was right on this, but then now this m factorial assumes that everything is duplicate. So I mean, and now we have free answer anyway. So okay, so let's try something like what I mean is that we have a free lookup on the answer because we already time expired. So yeah, so we know that this is going to be wrong because we don't divide it by the thing. But here that's fine because this is the part where we want to divide anyway, right? So it's this times inverse factorial of I, right? Yeah. Yeah, okay, fine. But I do want to flip this to. I mean, you don't want to. I guess 0 factorial is 1, so inverse of that is just 1. So, okay, that's fine, maybe. Okay, so I factorial is equal to x for, what's it called? Power to, power of what? Oh, just I factorial. So factorial of I, -1 on mod. I mean, I'm kind of writing this lazy, but it's only like 50, so it should be fine. It just be 52, something like that, right? Mod. Oh, I don't have mod outside. Okay, fine. I actually don't know how long I end up taking on this one, but okay, not right, unfortunately. Am I off by 1? Hopefully, I'm off by 1. Should be like 1 1. Okay, no, this is right. I factorial is right. Yeah, 1 2 3. No, that's 6, right? So 1 factorial, 2 factorial, 3 factorial. Okay, so this is right. Ish. What does 1 bit mean? I guess this part I thought I could work out, but clearly I'm wrong. I thought it was just I factorial. Huh. I mean, it's either that or my k left is wrong, honestly, which is it wouldn't surprise me, honestly. Just make it slightly faster, but maybe I don't know how to get rid of the tubes. I was hoping that this would be right, but I mean, a lot of things could be wrong on this one. So okay, fine. That's. I do want to get lunch, so I am struggling a little bit. But okay, fine. So 1 set bit, you have 2 amps, so I don't know, 110 maybe. I don't know. I'm just trying to see where I can figure it out. So expected answer is 101 because Why is that? M is, oh yeah, so it means that it is 10 and 10, and then 1 and 1, and then you sum it together, right? My answer is 1, so that's a little bit awkward. Why is that 1? Oh, no, no, that should be right. This should be right too. Okay, so that's maybe telling. Let's say I remove, oops, not that. Remove just this part. So then the answer is 2. So that's awkward. So I'm missing something. That might actually be helpful actually. Because why is it not doing 10 by 10? Okay. The 0, right? Okay, let's see. Oops. Okay. I thought it would be not too bad to be that was wrong. Okay. I mean, there's no 100 anywhere. Okay, so at 1, it should have 1, 1, 2, 1. So, okay, 1, 2, 1 is what we care about. Okay, fine. Carry is 0. That's fine. Total should not be 0. Okay, so why is it 0? What does it call? Yeah, that should not be 0. There's some optimizations we can make here for running time, but I'm just trying to do correctness, right? So everything is right except for the total. Okay, so that means let me. Alright, okay, right. Okay, so it's 1, 2, 1. So that's 0, 2, 0, 1, 2. So if this is, if I is 2, then we have 100 here plus, but then I minus 2, k left minus bit. Oh, the carry is wrong because I don't, oh no, I of 2, so that 1 is, oh, this carries. I see. So, I mean, it's, okay, maybe we're close, So then, okay, so, yeah, okay, so because carry can go outside the bounds, okay, fine. So then now, maybe, I'll just do it a little bit lazy, right? Is it bit count? Right, so we don't have to, we don't even have, okay, fine, just skip it this way. Is it underscore bit count? Okay. Or bit underscore count. All right. Of course, we have to try random things, not just the one that we did, right? I think if this is right, I will submit it. I mean, it may time out, but oof, that's tough. Okay. I mean, I think that definitely is a thing that we had to fix anyway, but at least we fixed it for one thing, so that's good. Okay, so then why is this still wrong? Okay, let's just do 3, 1, maybe. This. Alright, let's just do this. I think this is actually impossible. I thought it would be impossible, but it's not, because you can have 1 okay, so yeah, 1 times 1 times 10 is why it's not possible, or it's not impossible. So why do I get this one wrong? Everything is just 0, right? 1 3 1, so we want two ones and oh yeah, well, we have to do the ordering, but 2 1s and a 10, right? Okay, so that means that this one's impossible, which is correct. This one should, oh, wait, so we have a carry. I think this one should be, I gotta want to meet, like, this video is taking too long, so I have to maybe catch lunch with someone, so maybe I'll come back. But okay, so here index 1, m left, because we use 2, so we have 1 carry. K left is 1 because we used the 1 carry. Okay, that's fine. This should be non-zero. Okay, m left, so we want to use 1. What does 1 look like? So we have a bit, 1 converts it to 1, bit converts it to C, to, there is a carry, so bit is 0. Okay, bit is 0, so this is, K left is right. This is 0. Oh, I see. Okay. Okay, let's see if it's right for the other numbers, of course. Or just like this one. If it's right for this one, I'll submit it. But yeah, I'm really bad at math apparently. Okay. Yeah, it looks okay. Let's give it a YOLO submit. Submit. Ooh, yes. This is a ridiculous problem. How long did I end up taking anyway? I don't know. Actually, I mean, it's a rough estimate from the last time the last problem, because I did them back to back. I could look at the video as well, of course. But 49 minutes, that's not so bad. Thanks for watching, everybody. Hit the like button, hit the subscribe button, join me on Discord. Let me know what you think about this problem, this contest, this explanation, everything in between. Stay good, stay healthy, do your mental health. I'll see y'all later and take care. Bye-bye.